Adding projectiles, not too hard. Adding projectiles with a trajectory system may be a little bit more difficult, but really in Godot, it's super straightforward. And so by the end of this video, I'm going to show you not only how to make this cannon and cannonball, but how to get this trajectory line that predicts where the ball is going to fly. All right, so let's get started by looking at the scene I've built here. So I've got a simple world set up just with some tile maps, and they've got collision set up on them. Nothing fancy, just so that I have a place for these little cannonballs to bounce around. And of course, I've got this cannon right here. And let me show you how the cannon is set up. So the cannon consists of two sprites. The main base sprite does really nothing special. And then I've got this barrel, and you can see the origin of the barrel is set down here to basically the center of the cannon, or at least where I want it to rotate. So as I rotate this barrel in the game, it can move like so, okay? So let's go ahead and look at this script that I have attached to my cannon. And you can see that there's some things in here that I'm doing that provide functionality outside the scope of this cannon. So I've got some signals here that we'll return to, but just whenever we start aiming or end our aiming, and anytime our aim updates, okay? And I've got a cannonball scene that we can spawn. We'll look at that momentarily. But you can see here I'm getting a reference to my barrel. And really, it's pretty simple. I'm going to go ahead and just uncomment 2 lines of code here. And I'm going to use the barrel look at function, which will take a node 2D and it's going to rotate it towards a coordinate. And I'm going to just get the global mouse position. Now, this next line of code is important because of the orientation. I'm going to go ahead and comment it out real quick so you can see. By default, that's not quite pointing to my mouse, though it is rotating with it, right? And so when I come back in here, I just need to rotate that another 90 degrees. So I'm just going to add pi divided by 2 in radians, and that's going to be the equivalent of 90 degrees. And there we go. Now I've got a nice cannon barrel that's pointing at my mouse cursor. Okay. Next step is a cannonball. And let me look at this cannonball scene. It is a character body 2D, so that's the method I've chosen to use to approach this for a couple reasons. One, because it's just nice to give us the collision we need, and also I want to be able to use my own code for detecting or calculating the movement and velocity, because it's going to make it easier for us to calculate the trajectory when we know the exact code that we're using to manipulate and move the object. So here you can see it's a cannonball. It's got a sprite 2D with the cannonball. Of course, it needs a collision shape. And it's got an audio that we can play back when we bounce. And on this, we have a script. I do have an explosion that's this file right here, which let me go ahead and play back this animation for our explosion. Okay, so this scene is just designed to play this animation by default when it starts, and you can see here that it Q-frees itself. So it does the little animation, the sound effect, and then it frees itself. It's a very straightforward scene. But this cannonball has reference to that so that it can spawn it later, but it just takes a few variables to make it work. I've got some bounces so I can keep track of how many times it's bounced. After 8 bounces, I'm going to have it explode, and then it has a speed. This isn't the ideal way to make this happen maybe, but it's just a solution. And of course, I have a reference to my bounce audio. Now, what I've got going on, and I'm going to go ahead and just comment out this bounce code real quick so you can see. Really, this is pretty straightforward. So we're going to say our physics process is just going to update the velocity. So we're going to get the gravity, multiply it by the delta, and apply that to our velocity, and then do move and collide. And the reason why we store that as a collision variable is so that we can handle the collision down here later if we need to. But just with this change, let me go ahead and save that and come over here to my scene. And let's go ahead and just close some of this stuff. I want to add a cannonball into my scene so we can just see what happens. And where is this guy? There we go. Okay, so you can see we've got a cannonball. I'm going to go ahead and add a couple of these in different spots so that we can see what they do. Okay. But when I first run this with these, 4 cannonballs, they just fall and they hit the ground. Nothing special. They've only really got the velocity for the gravity happening. So if I go back to my cannonball and look at the script, we can see that what I'm going to do is I'm going to add this. If there's a collision, we're going to check for bounces. So let me just uncomment this code. I'm just going to increment the bounce value and play an audio every time it hits something. And then we'll just check, are the bounces greater than the max bounce? If so, then we want to Q-free it and spawn one of these explosion nodes that we have a reference to up here. And at the end of this section, if it collides, we do want to bounce it. So we're just going to use velocity equals velocity.bounce and use the normal of our collision, right? The direction that it's pointing. And this is kind of the dampening value, 0.75. You could export that value, but with that extra bit of code, now our cannonballs are going to bounce, okay? And they were starting to explode too. Let me just go ahead and tweak one of these. If I go back to my physics example, I think I want this guy here. I want him to be like right on the corner so that we can see that these do bounce in different directions. There we go. And you saw that they run into each other. Okay, so we've got a cannon that we can aim, and we've got working cannonballs with minimal code. Okay, we don't really want to just have cannonballs sitting here though, so let's clear those from our scene, and let's come into our cannon. And as you saw earlier, I do have a reference to my cannonball scene, so you can just drag in a reference to that. And then down here, let's just go ahead and add a little bit of code. And in fact, let me show you. I've got a script here called fire cannonball. And what it's going to do is it's going to play the sound effect, the shoot audio that I have here. Okay, it'll play that. And then we just create a new instance of a cannonball. We set its position, add it as a sibling to our cannon, and then set the velocity on that cannonball. Let's look at the fire position and the aim direction. We need to be able to calculate those for it to work. And of course, we need to be able to do this in an order that makes sense. And so I've kind of broken my code into a couple sections. So first of all, the unhandled input. Let's uncomment this. So you can see that if I press the fire button, which I just have bound to my mouse left click, then I set aiming to true and I emit an aim started signal. Now this aim started signal is not going to be useful just yet, but I also set a power. I've got this variable for power, aim direction, and fire position. So you can see that once I click, I set the power. And then when I release, I set aiming to false. I say aim ended. I emit this signal. And then I call the fire cannonball. And you can see one of the variables that we use here in the fire cannonball is that power variable. Okay, let's go ahead and uncomment this aiming code I've got here. This is also pretty straightforward. I just only run this in the process if the aiming value is true, right? So I set that here, right? I set it to true when I click and false when I release. This is going to allow us to click, let the power build up, and then release it. So then I'm going to derive my aim direction from the barrel rotation. And I had to add another 90 degrees to that. Just funky math. But I'm just going to get a vector 2 from an angle because I do want my aim direction to be in the format of a vector 2. Okay, because we're going to use it as a velocity and other things later. So the angle is less important in this circumstance. So we're going to go vector 2.from angle, and this will give us a normalized vector 2. And then the fire position, this is essentially just the global position of this cannon node, okay, which is right here, but we need to offset it so that it lines up with the barrel depending on the direction it's facing. So I just add my aim direction, which we calculate right here, a vector 2. I multiply it by the offset, which is 64 pixels. And I also have to bump it up 7 pixels because if we look at my cannon barrel, it's 7 pixels up here, right? You can see the position, -7. Okay, so really all we're doing here is we're just getting a position and then we're calculating where it is, where the tip of the barrel is, okay? So we've got our aim direction, our fire position, and our power. We're going to increase the power by 750 by delta, which means every second it'll increase 750. And we're going to clamp it to a minimum of 100, which is where it starts, and a maximum of 2000. And this could be adjusted. Okay, and then we're going to emit these, which again, we'll use that later. But now that I've uncommented this, we should be calculating aim direction, a fire position, and a power. So then when we come down here and look at our fire cannonball, we use each of those. We're going to use this fire position to set the global position of our cannonball. And then we're going to use the aim direction and the power to set the velocity. And here it's negative, otherwise it fires backwards. Okay, so let's run this now that I've got those uncommented, and we should be able to shoot a cannonball. And you can see if I tap it, it just barely flies. And if I hold it, it shoots a longer distance. Okay, now the one thing I haven't shown how we've hooked up is this nice indicator, right? That's flying out and showing kind of the trajectory of those cannonballs. So let's go ahead and look at how we do that next. Okay, now the trajectory is actually far more straightforward than you might think. Here I have a line 2D node, and you can see that this node, I have it visibility turned off. Let me turn it on. Okay, I've added 2 points to it just so we can see it. So I've got a point at 0, 0 and a point at 0 and negative 64 pixels, right? So up 64, which is going to give us this line. I've also got a width curve turned on. And what this width curve does is over the course of the line, it defines the width of that line. If we don't have this variable, then it's just a straight line like that. But this width curve going from 1 to 0 will give it that nice point. And then I simply have a color defined, which is just a basically white, a very light yellow. And that's all you need to do to define and set up this curve. And I've moved it and positioned it on top of my Canon, but ultimately it doesn't matter. It could be over here. Our code's going to pop it into the correct place. A couple other things I guess that I've done is I did set the Z index to 10 so that it's on top of everything. But you can set it whatever you need it to be for your game. I have some variables here, the line points and time step, which will show you those are part of our trajectory code. So if you look at the trajectory indicator, this line 2D, it has a script attached. It's called trajectory indicator. It extends a line 2D. Here are the values that I export. And essentially what this is this line draws straight points, right? You can see that this is just a point from 1 to 2. So in order to get that smooth curve, we need to draw multiple segments, okay? And so the line points controls how many points we'll draw or how many segments there are. And the time step is used in a simulation, okay? So by default, I have my line point set to 20. You can see I've adjusted it here in my inspector to 15. Likewise, I had the time step really low, but I've adjusted it to 0.04, okay? So let's look at how those work. In order for this script to work, we obviously have these variables. We also need to get our gravity, and I'm just going to use the project settings gravity, which for a 2D project is equal to 980 by default. And then lastly, I do have a reference to my Canon script, which we looked at earlier, okay? Because this script has the signals on here, and we're going to utilize those signals to make sure we update our line accordingly. Back to our trajectory indicator. So here in the ready function, I'm first going to clear all of our points, which if we were to demonstrate that right now with this, clearing the points would be essentially that. There's no line, okay? But I'm going to go back to my script. We'll clear the points. We're going to make this not visible by default. And then we're going to connect to these 3 signals that I have on the Canon. So we're going to have a listener for the aim changed, aim started, and aim ended. Let's start with aim started. On aim started is the function we call, and really all we do is set the visibility to true. Likewise with aim ended, we have this on aim ended function, which sets the visibility to false. Okay, so that's just going to toggle on and off visibility when we click and release the mouse button, right? If we go back to our Canon and look where we emit those signals, it's when we click and release the fire button. Now the last signal is emitted here in our aiming part, which is in our process function. So we can see during the process, if we're aiming, then we're going to constantly emit the fire position, aim direction, and the power. So if I go back to my trajectory indicator and look at this on aim changed, which handles that signal, you can see I'm going to set the global position to the position I pass in, which let's review the code real quick one more time. Okay, so this fire position is what we calculate to be the tip of the barrel. And then next we pass in the aim direction and the power that we've calculated here. So if we go back, you can see we're going to every frame clear our points, and then we're going to start by adding a point at vector 2, 0. Because since we've positioned this trajectory indicator in code, if the barrel's rotated, then this origin of this object is going to move with the barrel, right? So the first point is at 0, 0. And then we're going to store that as a current position so we can begin kind of calculating each point over time. And you can see we have a velocity. We'll calculate our velocity. It's just our negative direction times our power, which is the same formula we're using down here when we set the velocity of our cannonball, okay? So you can see how that's basically the exact same code, and it's very simple. Then what we do next is we iterate over the number of points that we want to. So you can see we have our line points, which is default 20, and you can see, again, I've set to 15. So this is going to happen 15 times per frame, and what we'll do is we're just going to take our current position and then we're going to increase it by the velocity times the time step. And what this time step is telling us is like, how much time do you want to simulate, right? So we're going to say, let's simulate 0.01 seconds, or in the case of the value I've set here, 0.04 seconds. So if we multiply our velocity by that time, then we'll have a distance that we can change our current position by, right? So we take that distance, add it to our current position, which gives us the next point at 0.04 seconds in the future where this line should be if the ball were flying through the air. So we'll add that point using this add point method, which is just a native method on the Line 2D, right? And in fact, let's go ahead and look at this real quick. If we look at add point, we've already called this twice. It just adds a point with the specified position relative to the polyline's own position, okay? And if no index is added, which we're not, then it's just added to the end of the points array. Okay, so we're going to add a point, and then we're going to calculate the velocity change according to gravity. So we'll do kind of a similar thing. We're just going to increase the velocity y value by the gravity times the time step again. And then because this is a loop and it's going to run 15 times, right? Then it's just going to keep making a new position, adding it, calculating the change in velocity, rinse and repeat until it's gone through that loop, that number of points that we've desired. And the end result of this is that as we're holding down the button, it's going to continuously draw this line that grows, and it's going to calculate what that trajectory would look like for this ball over time. And then whenever we let go of it is the velocity and the trajectory that we get, right? So pretty simple and pretty straightforward. I hope this has given you some ideas on how you can implement a trajectory style system into your own game. It is a lot easier when you're calculating the physics or the movement of your objects, because then you can write your trajectory code to match. But if you're using the physics engine, you should be able to kind of do the same type of calculation. You just have to be aware of things that you might have added to your cannonball. Things like movement damping and other things like that will affect how that ball is going to move through the air. So thank you for watching. If you're new to the channel, drop a like and subscribe so you can see what's coming next. Right now, the next big thing on the dock for me is to move on to a new chapter of a long-running series I've been working on, which is the Metroidvania Forge series. In the next chapter, we're going to be focusing on enemies and enemy AI. And if you're watching this video within a week or two of me posting it, then I'll put in the description a link to a video where I have a contest going on for enemy designs for the Metroidvania Forge series. So if you're a pixel artist or a budding pixel artist and you want to submit some Metroidvania-style enemies for my little showcase, then please hop in and do that. And with that, thank you for watching, and we'll see you next time.